focus on. So on Monday, we spent a lot of time talking about the role of vacancies and precipitate-free zones and heterogeneous versus homogeneous nucleation and different heat treatments of where you quench. And we left off talking about what makes a good age-hardening system. And the big ones are Solvis line curvature, right? Ease of homogeneous versus heterogeneous precipitation, right? And the fact that heterogeneous precipitation is primarily going to occur on dislocation and grain boundaries, right? So when we say a strongly curved solvis, right, we have here, where if we're above, we're in the single-phase region. If below, we're in the two-phase region. So this is the solvis line for the secondary phases here. All right. Why is this important? Well, if we didn't have a strong, the degree of curvature that we have here is directly proportional to the amount of solute we can put in our system. The amount of solute is the amount of particles that we have available for reinforcing, right? If this was like, say, basically a line compound, right? We can only have a very small fraction, like iron carbon. We wouldn't be able to get a large amount of secondary phase reinforcing particles there. So that this solvis curvature is really like a first order alloy design criteria. Right? So on the surface, aluminum magnesium looks like it would be perfect. It has that strongly curved solvis. The GP zones, though, are spherical in shape. Right? I think the last thing we talked about on Monday was that the lattice parameter for aluminum and magnesium were much closer, right? And the shape of the GP zones was driven completely by the elastic anisotropy, right? So the platelet shape developed to minimize the strain energy of the particle, right? So if we have elements, solute elements where the lattice parameter is much closer, the strain field around them is much lower, and so we can have spherical particles, right? Why is it going to be a spherical particle in the absence of strain? Because the sphere minimizes the surface area per volume, right? Even though it's still a coherent interface, there is still a penalty to pay, right? An interfacial energy, right? So a sphere will always minimize that, right? Classic bubble physics, right? Okay, and so if we have low magnesium weight percent, the solvis tends to be lower than the room temperature. If we have a higher magnesium weight percent, the solvis is at or above room temperature. When we talk about the commercially relevant alloys, we'll see that high weight percent magnesium alloys tend to be cast alloys. And really, these tend to be used in the lower weight tend to be used in a solid, near solid solution state, and generally very high work hardening abilities, very good formability in these alloys, which is why they tend to get used a lot. But of course, the issue comes about with the phases that form, especially at high weight percent. So the intermediate phases after the GP zones is beta prime. This is a hexagonal structure, right? With a C over A ratio pretty close to ideal if it were a single single atom type, right? But what do we notice right away about this? Aluminum's FCC beta prime is hexagonal, so that means it's going to be incompatible, right? Our lattice parameters are quite different. The lattice parameter of aluminum is 1.4. This should be right. 0.14, right? 1.4 angstroms. I'm getting my units wonky, right? So this is a big unit cell, right? The lattice parameters are very large. So this is going to be nucleate completely heterogeneously, right? So primarily on dislocations and grain boundaries. It is going to form with a preferential orientation relationship, right? This is the first time I've mentioned an orientation relationship. It's going to be really important for steels, right? Remember, in steels, everything tends to form with what we call a Kirchhoff-Sachs orientation relationship. Right? And we'll spend a lot of time detailing that specifically. So what does this notation mean? Right? So what it's telling me here is that the 0001, the basal plane in beta prime, is parallel with the 001 plane in the FCC, right? So the basal plane and the cube plane are well aligned, right? The cube face plane. And then the 01 bar 10, what type of plane is that? What do we call? It's a hexagonal. Prismatic plane, right? It's a prism plane, right? Oh yeah, sorry. Yeah, these are planes, directions. I got to look at my own notation. I got brackets here. Sorry. Right? So we've got the got an A-type direction parallel to the 110 direction in the alpha, right? And so what these orientation relationships tell us is how that interface, represents a low energy interface configuration between those two at crystals, and it's going to tell us which atoms or what the atomic arrangement of that interface always is, right? So I threw a statement in here, so the occurrence of this orientation relationship indicates that the intermediate phase is probably semi-coherent. Right? And then I have a leading question here, why? That's something I want you guys to think about. How do I know this isn't really coherent? Or, right? We can say, if it was an incoherent interface, are we likely to observe any preferred orientation relationship? Right? No. Right? So how can we be certain that this is not going to be a perfectly coherent interface? Right? And the answer is pretty simple, so don't spend a lot of time thinking about it. Yeah. But you could potentially have a coherent relationship between HCP and FCC if the basal, if you have the right, if the close packed planes are parallel and the lattice parameter is good, right? Right. So think about it. It's a really simple idea. If you can't think about it right away, just make a little sketch of the atomic positions, and you'll see it. You'll see it right away. The stable phase, beta. This is really important. Technologically important phase because when it appears, bad things happen, generally. Right? We want to avoid formation of beta. Right? It's got the composition Mg5Al8. Older papers listed as Mg2Al3, which is what I thought the composition was. It is a FCC like ordered phase. It has a parameter of 2.824 nanometers. Why is this significant? It's a nice multiple of the aluminum lattice spacing. All right. Oh, that's weird. This is going to nucleate heterogeneously as laths or plates, primarily at grain boundaries, but it can also nucleate on the surface of the beta prime particles. Right? It has an orientation relationship, and it forms incoherently, so I'm being inconsistent with my logic. It has shoot. I just made an argument on the previous page, and then I contradict myself on this page. It has an orientation relationship primarily because you have these sort of low energy planes when it nucleates at the surface of the beta prime particles. All right. What's the real? These orientation relationships, again, are not important for you to know either. There's only one orientation relationship that you have to know, and that's the Kirchhoff-Sachs steel and the next thing. So don't worry about memorizing these. It's just I thought it was important to put down there when certain phases form with orientation relationships. So why did I say this beta phase is really bad? Right? So those of you in the corrosion group, any of Professor Locke's students in here? All right, so why is beta? Yep. Yeah, so it nucleates heterogeneously at grain boundaries at relatively low temperatures, and it tends to form nearly continuous phases continuously on the grain boundary, really susceptible to stress corrosion and cracking, right? So the Navy is actually having a huge problem with this right now, right? They built a bunch of ships 20 years ago using magnesium-containing aluminum alloys, and then left them in the tropics for several years, where the temperature was hot enough and the kinetics just fast enough, so over that period of time, grain boundary beta was growing. And now they're having huge problems with stress corrosion cracking because you're in salt water, right? You're in a horribly corrosive environment. And while aluminum forms a oxide layer that's really good at preventing corrosion, right? The electrochemistry of aluminum is really, once you get through that layer, right, it wants to return to dirt pretty quickly. Right? The Ellingham diagram for aluminum is right, and now you're putting in dissimilar metal galvanic cells, right, along every grain boundary, right, and they're brittle and they crack, and hydrogen embrittlement's really bad, right? So this is the danger of aluminum with too much magnesium in it. It does provide a really good solid solution strengthening. Why do we use it, though? It reduces density, and provided you can avoid beta, the magnesium doesn't affect corrosion properties. Right? Aluminum copper, on the other hand, is highly corrosive, even in this, corrodes very quickly, even in the solid solution state. So aluminum magnesium, it seems odd that you put magnesium in something to make it better at corrosion, right? And now we've just essentially eliminated all of my knowledge of corrosion in aluminum alloys. So don't ask me any specifics, right? But it is used commercially, right? So when our heat-treatable alloys, we tend to keep the magnesium content less than 3% so that we avoid the beta, right? Intergranular corrosion reduces mechanical properties, right? Aluminum mag silicon alloys, these are the basis of the 6000 series alloys, right? Everyone who has a bike frame, that's aluminum, right? 6000 series aluminum. Right? The GP zones are needles along the 100 direction. Right? Amazing what throwing a little silicon in there tends to change them from perfectly spherical GP zones to needle-like GP zones. Right? And the solvus occurs at temperatures that are above the aging temperature. So the addition of silicon raises the GP zone solvus temperature above the typical use temperature. So that means we can get a refined precipitates and have good strengthening in these types of alloys. Right? So the intermediate phase is again beta prime, Mg2Si with a hexagonal structure. Right? Semi-coherent rods. They nucleate heterogeneously on the GP zones, has a orientation relationship, right? The stable phase is also a beta phase with this FCC, has a much smaller lattice parameter than beta in plain aluminum mag, and it forms as platelets directly from the beta prime. Right? So the presence of silicon changes the precipitation sequence, right? So it's a completely different class of alloy, the 2-component versus the 3-component magnesium aluminum silicon, right? And these are, when we look at the commercially pure the commercially relevant alloys, I'll talk a bit more about why this Mg2Si will be explained later. But really, we think about this not as a ternary, but as a pseudo-binary, meaning we have a 2-component mixture of aluminum and magnesium to silicon. Right? If we treat this as a second element, this precipitation sequence essentially then follows what we get for aluminum copper. It's the same set of steps, right? Aluminum zinc. So the aluminum mag and aluminum mag silicon are also used, and again we'll talk about this next week, right? Also used because they have good weldability, right? We can join them. We know what to do with them, right? So very important if you're making bicycles or ships, right? That you don't have to cast an entire bicycle out of one piece. You can make tubes and weld them together. Well, other people can. I'm horrible at welding, especially aluminum. Right? I just blow holes through aluminum. I get all excited. I'm like, ooh, I hit a bead. And then I'm like, oh no, I have a hole. And it's instantaneous. There's no in between. Aluminum zinc is really interesting, right? So we have a very highly curved solvus, significant maximum solubility, 16.5 atomic percent, right? But we've got something else going on here. What's going on in this part of the roof? Right? Alpha and alpha prime. What's this region? It's got a very important word, two-word phrase, MG, miscibility gap, right? Right. So if we're in this region, we're actually in a two-phase regime of alpha and alpha prime, and so we have a spinodal decomposition that occurs. Right. So alpha prime is actually a rhombohedral structure. Compositions between 60 and 70% atomic percent zinc. Right. So if we look at the phase diagram, if we're above here, we have a continuous transition from FCC to rhombohedral. If we're at a slightly lower temperature, we have a phase separation by spinodal. EP zones are spherical and ellipsoidal. So ellipsoidal is kind of intermediate to the plate, right? There's elastic anisotropy, but it's not driving to a rod or plate structure. Zinc is fairly close, closer in misfit to copper, but not as close as magnesium. 1.38 angstroms to 1.43, right? And so this accounts for the shape of the zones, right? So aluminum zinc has some intermediate precipitates, right? Rhombohedral structure. There's a whole suite of these, right? And we also have the incoherent alpha prime, but we don't use this. These are not really commercially very important, right? But basically, we can get significant hardening out of these because we have a very nice refined dispersion of spherical GP zones with that 3.5% misfit. We can get significant hardening out of these systems, but I don't want to spend a whole lot of time on them. But it leads into a very important. The curiosity here is just because of the miscibility gap. If it wasn't really for that, I probably wouldn't have bothered to throw them in there. Aluminum, zinc, magnesium forms the basis of a 7000 series alloy, and we'll spend a lot of time talking about specific instances of this. But out of this has essentially the greatest potential for age hardening out of all the aluminum systems. We have generally spherical GP zones, and we saw that aluminum zinc and aluminum magnesium both exhibited spherical. In the case of aluminum zinc, it could also be sort of ellipsoidal GP zones, right? But here we have spherical zones. I threw in the ternary phase diagram. I forget at what temperature this is, 500 K. But you can see there's a lot of things going on in here, right? It's not a simple phase diagram by any means, right? And I know I hate reading ternaries, so I'm not going to ask you to do it, right? But you can see all the different phases in there. So if we look at the intermediate phases that can appear, we have this eta prime phase, we have a hexagonal phase, eta, which is also a hexagonal phase, right? So this is going to, the eta prime can form from the GP zones if the zinc to magnesium ratio is high enough. If it's not, it'll nucleate heterogeneously. Other places, eta is going to form at or from the eta prime, right? And eta is interesting because it has a whole set of orientation relationships. It's got a whole, right? There's a whole suite of relationships that it could potentially have, right? Oh, interesting thing. I just realized I don't have it in here. And I didn't talk about it last year either. So we saw it about the orientation relationship in aluminum mag. Right. And I believe, okay. So this is an aluminum germanium alloy. This also is going to have an orientation relationship. If the orientation relationship exists, why do I have particles that appear to be facing different directions in the micrograph? Right? If I say I define an orientation relationship and I say this plane is always next to this plane and this direction is parallel to this direction, how do I have precipitates, if this is a single grain, how do I have precipitates that are facing different directions? Right? Remember, these are crystals, so we have symmetries. So the matrix phase has symmetric equivalence. There's how many ways can I rotate FCC and still, right? I got threefold rotation on the 1-1-1 plane, so I got 12 different orientations of the cube that leave me with the same atomic structure. I also have the same for my precipitates. I have the symmetries of those. So basically, these are different variants, right? They make the orientation relationship. They all satisfy it, but they're different rotations in space, right? They're different. It's a different crystal orientation, but they satisfy the orientation relationship. Those are called variants. We'll talk about that a lot in steel when we talk about martensite. So from austenite to martensite, we have 24 variants. They all satisfy the same orientation relationship. I just thought I'd throw that out there when I was talking about this, because I want to point out that the variants are different than having multiple orientation relationships, right? So what this means is that there are preferential ways for this phase to grow, but they're not so also different in energy that you see one over the other, right? And this isn't necessarily all that uncommon when you get into lower symmetry systems. For example, in zirconium has a high pressure phase, and there's multiple orientation relationships observed for that. So these 9 orientation relationships that I say here are different than the variants, right? And I want to variants of a single orientation relationship. And I wanted to just throw that out there in case anyone got confused. We also have this T prime and T phase, different compositions that form coherently and incoherent. Again, with different orientation relationships, right? And we'll talk about these precipitation sequences more when we get into the specific alloys, right? But again, don't go memorizing these. Don't memorize what the particles are and whether or not it's Mg32 aluminum zinc 49, right? That's pretty useless, right? What are you going to do with that, right? The idea is the idea that I want you to come across with is that in these aluminum, zinc, magnesium alloys, I've got a whole bunch of different phases. I've got a really complicated phase diagram when I think about how to optimize this or what phases are going to be present. My processing is going to be really sensitive, right? Because I'm going to have all these different phases coming in and out depending on the temperature and what's been done to it previously. Those are the kinds of things I want you to think about, not memorize what phases are there and what their composition are, because that's a pretty useless thing. You can look that stuff up in a handbook, right? Okay. Aluminum. Lithium is the last sort of family and sequence that I want to talk about. I put a reference here. I'll put this paper up on Carmen. D.B. Williams, Microstructure Characteristics of Aluminum Lithium Alloys. Who's this D.B. Williams guy? That's our dean, right? So did anyone not know our dean's a metallurgist? Microscopist? Wrote the book, Williams and Carter, the textbook on electron microscopy, or one of the most famous textbook on electron microscopy. And he did a lot of the really early work with aluminum lithium alloys when he was at Lehigh. So this is still a really good paper, even though it's a bit dated. The micrographs are kind of old, but it has a lot of really good information in there. Why is aluminum lithium really of interest, right? So because two things, right? It's pretty light, right? And also, lithium has this really neat effect on the modulus of aluminum, right? Adding lithium greatly can increase the effective stiffness of aluminum. So you get very stiff alloys with a pretty significant reduction in density, right? So really good for aerospace applications, all right? So the stable phase in aluminum lithium is this delta phase, which is a B32 structure, right? 16 atoms per unit cell. This just gives the positions of all the atoms, right? And so this, to me, doesn't look very much like FCC, right? Does it to anyone else? It's a pretty big unit cell, right? So, of course, that's going to suggest heterogeneous nucleation, right? So the stable phase is going to nucleate heterogeneously, but we can nucleate metastable delta prime, right? When we age supersaturated alloys, right? And what does this look like? Right? It's an ordered phase, but it looks an awful lot like FCC to me, doesn't it? Right? So L12 crystal structure, right? So this is essentially FC. This is a super lattice ordered compound. We'll see the same structure when we talk about nickel superalloys. This is the same structure of the gamma prime phase. The misfit is very, very low. So we have a good fit structurally that permits a very fine homogeneous nucleation. Right? So these are the kind of ideas that I want to get across. Right? So if I gave an alloy on the exam, and I didn't tell you what the element was, but I said this is the equilibrium phase, this is a potential metastable phase, these are the size mismatch of the atoms, right? And I could then walk you through a question that says, okay, on the small undercooling, right? You're trying to design this for strength. What do you want to do? Right? And then I can walk through and say on a small undercooling, what is the microstructure going to look like after a long aging time, right? And of course, we're going to nucleate this bad guy heterogeneously at the grain boundaries, and it's going to be a pretty useless microstructure for us. But because the misfit of this is so small, right, is there really a big barrier to overcome to nucleate this, right? The misfit's 0.08%, right? So these are gonna come together no problem, right? So we're going to nucleate this really easily, and then we can coarsen them, grow them to the peak age state by coarsening, right? So so what I want to point out here, so this is a very refined dispersion of the delta prime particles in aluminum lithium alloy, and this is in the as quenched. I haven't aged this, right? So just quenching allows the formation of these particles, right? Which we can then grow to nice spherical particles by coarsening, right? So there's, if you look in the literature for these, there's a lot of confusion about this delta prime solvus. And that's because particles that were nucleated coherently or incoherently, right, depending on the interface type, whether they were nucleated homogeneously or heterogeneously, they're going to have different solvi, right? So heterogeneous on dislocations tend to give you an incoherent interface, which then have those particles have a higher solvus than those that nucleated homogeneously with a coherent interface in the grain. Right? On subsequent aging, these are of course going to coarsen. Right? The coarsening is going to occur more rapidly on dislocation. I threw up the kinetics for Oswald ripening on there. Again, K is going to be a term that depends on the diffusivity and the interfacial energy. Right? And what happens during Oswald ripening again? Right? The big particles grow at the expense of the smaller particles, right? So we involve diffusion, right? And of course the surface energy, and then the particle size, all right? And so if we age it for 2 hours, we can see here we've got a dislocation running through here, and these particles are coarsen. All right, whereas in regions where we don't have any dislocation, they haven't coarsened quite as quickly, but they're still significantly larger than the as quenched structure. This scale bar is 0.1 micron. This scale bar is 2 microns. Right, so 20 times difference in magnification. Right, so we still coarsen, but when we're on or near dislocations, they coarsen much more rapidly. What's the cause for that? Easier diffusion along the grain bound. I mean the dislocation. Yeah.
I know lithium is already reactive with water.
Yeah, I don't know the what exact routes you can take. I know a lot of them are powder metallurgy alloys, right? But I don't know how the stock powders offhand are made, right? But I can look that up, right? And it's, yeah. I've never worked with this alloy system. Corrosion groups, you guys, Professor Buckheit's students did a lot of aluminum lithium work. Any idea? Okay. Right. So this is what we were saying. Formation on grain boundaries and dislocations. Right. No. This is delta, not delta prime anymore. So the formation of delta is going to form on the grain boundaries and dislocations. So the growth of the delta phase is going to come at the expense of delta prime. Right. Formation, as we recrystallize, tend to form precipitate-free zones along the grain boundary. And then there's a neat little thing in here called cellular coarsening, where you change, go to a discontinuous coarsening reaction rather than continuous like Oswald ripening. And the mechanisms behind this are not important for anything that we're really going to talk about. But what you can see is changes in the morphology of the precipitates, right? So here we have these sort of uniform, fine dispersion to this string, elongated, much coarser structure, and this is a result of this cellular coarsening. And it's something that's not necessarily easy to predict, and it's bad, but it doesn't happen very often because the driving force for it is low, and commercial aluminum lithium alloys have other elements in there that completely suppress this. So it's not something that we really have to worry about. Okay, so the last bit that I want to hit on today is I mentioned that lithium, one of the main reasons why this is so interesting is because it really gives a big increase to the modulus of aluminum and makes it stronger, right? So when I say it increases the modulus, I mean the effective stiffness of the sample, right? Because there's nothing I can do really to change the bond stiffness between aluminum and aluminum, right? But in a composite, I can change the effective stiffness by putting in phases or particles or other type reinforcement. So if we look here, this shows the stiffness, Young's modulus, as lithium content, right? And you can see essentially you get a pretty big boost, right? And so this here is the reference stiffness for aluminum, right? This is the increase you get in the solid solution regime, right? So what does that tell you if you're increasing your stiffness in the solid solution regime? That aluminum lithium forms a stronger bond than aluminum and lithium, right? And right, so we're changing the stiffness there from that, and then this is essentially particle reinforcements from this delta prime, right? Remember, the delta prime was an ordered structure, right? So when we have that ordered structure, we have an aluminum completely surrounded by lithium, and lithium's completely surrounded by aluminum. So we're maximizing our probability of the stronger bonds forming, right? And so that's why we're able to get such a big increase in stiffness out of this system, whereas when we talked about aluminum copper and aluminum magnesium, we didn't talk about changes in moduli, right? It's very little. Okay. So, in summary, the last slide for today, for aluminum lithium, if we overage, right, we can form the delta. We have coarsening. They switch to this discontinuous coarsening, formation of precipitate-free zones. All right, so in the overage state, this is going to give us a big reduction in strength and is detrimental to lots of other properties such as toughness, because the equilibrium delta phase is going to be brittle, right? Delta prime precipitates offer a lot of hardening, but because they're that ordered structure, we have a nice refined distribution of precipitates, right? Remember how we talked about when you have a coherent structure that's easily cut, we get the localization of slip. We have a precipitate that's cut by a dislocation, then another dislocation follows behind it, right? Because we have sources that lie on the same slip plane, right? And so this becomes a significant problem and can lead to softening and give us stress concentrations. I threw in the one line there, right? The reactivity of lithium gives us processing problems. But it's kind of like when you read a paper on aluminum lithium alloys, it's like a sentence that's in the first paragraph. And then because we're talking about mechanical properties, it's never elucidated on. So I will do a little research there and come up with a satisfactory answer to your question. All right. We get a 3% reduction in density per 1% of lithium addition, right? And an increase of 6% in elastic stiffness per 1% of lithium, right? Up to 4% when it starts to go off. So there's a lot of possibilities here. The aluminum lithium space, and to a lesser extent, the magnesium lithium space is really an active area for structural metals. There's a lot of gains that can potentially be made there. So that's why I spent a little bit of extra time on it.